The gravity of the time is such that every new avenue of peace, no matter how dimly discernible, should be explored. Never before in history has so much hope for so many people been gathered together in a single organization. You will provide a great share of the wisdom, of the courage, and the faith which can bring to this world lasting peace for all nations and happiness and well-being for all men.
So we are here today on Titans of Nuclear with Armando Nava-Dominguez, who is the technical lead on the Supercritical Water Cooled Reactor Gen 4 project at Canadian Nuclear Laboratories. Armando, thanks for joining me today.
Thank you very much. It is my pleasure to join this interview. I'm very excited. Let's do it.
Yeah. Okay. So why don't you start off by reading this this important paragraph, and then after we do that, we're going to get back into your background and story. But this will be a great way to kick off the episode.
Sure. The reason I want to read about this paragraph or read this paragraph is because I noticed that a lot of people do not know exactly what it means, supercritical. And unfortunately, the word critical is so universally used in different terms. In electronics, a critical reactor, but it's mostly related to criticality. We have critical heat flux that is related to thermalhydraulics. There's multiple uses for this word, but here what I want to explain is really what is critical about supercritical. And I found a very interesting paper from the 90s that explains that in a very short paragraph. And it says there is nothing critical about supercritical. Supercritical is a thermodynamic expression describing the state of a substance where there is no clear distinction between the liquid and the gaseous phase. That means they are a homogeneous fluid. Water reaches this state at pressure above 20.1 megapascals. What it says, there is nothing fancy about supercritical conditions. And actually, supercritical fossil fire plants, they have been operating at supercritical conditions since the 1960s. Then this technology is mature. It is available, and is nothing that we cannot achieve. It is a proven technology.
I honestly could not agree more. And this is why I've been trying to drive to find someone like you to explain to me why this wasn't the natural progression of PWR and BWR technology, as opposed to, why everyone feels like they need to advance the nuclear technology development roadmap by throwing water out the window and switching to a different coolant, when the coal industry has already proven that you can get your higher temperatures and higher efficiencies with water.
That's right. And I have to be honest, I have been fighting this battle for some years, and you're right. Imagine, this is my vision, and this I will share it with everybody. Imagine if we can replace all supercritical fossil fire plants with a supercritical reactor.
Yeah.
Like we have the best of the two technologies.
Or just even normal coal plants that operate at, let's say, like 500 C with a supercritical 500 C PWR or something.
That's right. And that it will help a lot, because then you can use what is already there, the equipment that is already there, the expertise from the utilities that not only operate water reactors, but also that operate fossil fire plants. For me, there is a no-brainer. This is an excellent transition to help with the gas greenhouses emission. This is one for me, and this is the reason I like this supercritical water reactor, is because there is actually a transition plan here. We can evolve as the supercritical fossil fire plants evolve. The fossil fire plants evolve from subcritical to supercritical, and now they're talking an ultra supercritical. If we can do that in a nuclear reactor, I believe it will be a game changer, because we can use what is already there, but most importantly is the experience.
Yep. Yep, absolutely.
Experience
I know.
is, there is a quote
Supply
by
chain
Alex.
experience, de-risked. It drives me crazy when everyone wants to just launch towards the unknown when there's a known way to solve a problem.
That's right. There is a quote that I love from Albert Einstein, I believe. He says that knowledge is experience. Everything else is just information.
That's
And
awesome.
here we have 70 plus years of experience with water cooled reactors, 70 plus years with supercritical fossil fire plants. If we combine them, we can have an excellent platform to really help the planet. And we can replace those old fossil fire plants. We maintain some jobs. We extend these capabilities. We have the codes. We have basically the majority of things that we need to make this happen.
Okay.
Why we want to change to another technology?
Yeah, I know. Okay, well, let's come back to that because I actually do want to pull apart and analyze like what your interactions are with other people and what those debates look like when you have these discussions. But before we get too far ahead of ourselves, we'd love to learn about you as an individual. Can you start off by telling us where did you grow up and how did you get into the nuclear industry?
Yes, definitely. Well, I'm Mexican. I was born and raised in Mexico City. Um, that was in 1975. Since I was a little boy, I was passionate about energy, the universe, time. I remember going to the high school and asking my professors, like, what is time? Why are we living the present? What is the time of present? And they were telling me, these kind of questions are very difficult to answer. And actually, they may not have an answer. So focus on something else, something that you can manage, concrete. And then little by little, I start studying more energy. By the end of the high school, we had to choose our major. And somehow I found a very interesting program in the only university at that time in Mexico that gave the program of energy engineering. I said, well, I applied and I was accepted. But I had to make a lot of sacrifices because my best friends, they were going to different universities, and I decided to go to this one alone. I always studied in a private schools, and this one a public university. I decided later I will give it a try, and actually it was an eye opener experience. I started studying energy. It was amazed. I loved thermodynamics. I took all the courses that I could in thermodynamics of systems. And by the end of the program, I had to focus on very specific parts of the degree. And we had renewables, energy management, thermodynamic of systems, and there was also nuclear. But I was not really interested on that. I was more like I wanted to continue studying thermodynamics. But one professor came from Laguna Verde, the power plant in Mexico. He says, well, I can help you. I know you love heat transfer, thermalhydraulics, fluid mechanics. Why you don't give a try to this technology? I said, well, why not? And yes, I decided to start my path in nuclear. I love it. I learned a lot. At that time, I had to do it by myself, no CFD, nothing. I had to learn to program in Fortran and use the old subroutines, BlaBlaS, LAPAC, and all these kind of things. I really enjoyed it. It was heavy, but I really enjoyed it. And then somehow I had the opportunity to come to Canada. And I went to École Polytechnique of Montreal, a French university. And by chance, I met a professor in thermohydraulics, and he told me, Armando, do you want to study here? And I said, yeah, why not? And say, bring me your notes and let's see. And I went back again to the university next day. He looked at my notes and he says, just let's go and talk to the lawyer, because I was still studying only languages in Montreal. And he told me, you sure you want to study here in Canada? I said, yeah, that will be my dream. And I would love to do that. And the lawyer says, okay, I'm submitting your papers and you're officially now a student. And here we go. And the professor told me, well, you start tomorrow. And I said, what? I said, yeah, you start tomorrow because the classes started 2 weeks ago and you start tomorrow. I said, but I don't speak French. I said, you start tomorrow. And then, yeah, that was my I had to learn French on the way. It was not that easy. And after that, a few months later, a utility in Montreal, Hydro-Quebec, in Quebec, the province of Quebec, called. They needed some people. I how can say, I went there. They interviewed me, and after a few months, they told me, "Well, come here," and I started a program with them, and it was exceptional, a beautiful team. I had the opportunity to work in the safety and reliability section of the Gentilly 2 nuclear power plant in Montreal. Beautiful. I had the best hands-on experience on nuclear power plants, especially CANDU reactors, the Canadian reactor. And finally, when I finished my master's, they asked me to apply for the Chuck River Laboratories, so the Canadian Nuclear Laboratories, and I submit my application, and they probably a month later they call me for an interview, and they also accept me. And what it was interesting is that they asked me to continue doing what I was doing in my master, that it was subchannel analysis of thermalhydraulics of fuel assemblies. And I decided to say, yeah, why not? And I'm here since then.
Cool. That's
Yeah.
great. So, and how did you decide to focus your studies? Like what or your research, I should say?
Well, that life has been giving me that path, and I don't know how, but I remember when I started in Mexico, studied heat transfer and thermohydraulics. The last class I had, it was about subchannel analysis, and the professor said, "Well, this is the last lesson today. We finished the program with this. This is a more advanced topic, but I will give you some ideas of what is a subchannel analysis." And it finished there. When I went to Montreal, it happened that the professor who accepted me worked in that field. He gave me to continue that as a project. But on top of that, he asked me to start studying genetic algorithms. And those algorithms that are based on like mimicking nature to optimize process, it was beautiful, because then you just combine not just the science, but also you understand a little bit more about the evolution of the planet, of the species, why we change, how to find the optimal point. Very interesting. And that it really helped me to have a better view of, I would say, our planet, how energy is the element that it is needed to evolve our society, or each individual. Energy for me is basically everything, and we need it, but we need to be very careful of the type of energy that we use to manage it, because the byproducts can be also very harmful to the planet and to ourselves. But basically, that's it. Yeah.
Cool. And then, so the subchannel analysis, this became your first focus area, or the biomimicry stuff?
It was my first focus in subchannel analysis.
And what is subchannel analysis? Can you just quickly describe it to our audience, what that study is?
Yeah, I will show you something. I have it with me.
Okay.
This is a CANDU bundle.
Oh, I love it. I love it.
And what I try to study with the subchannel analysis is how the fluid behaves inside of this fuel bundle with the elements. We discretize this section into small subchannels, like small passages, and we try to predict the thermohydraulic behavior of the fuel assembly. This is for
and when you say thermohydraulic,
reactors.
do you primarily mean heat transfer, or does it include everything like turbulent flow and other things as well?
That's right. Yeah. What we try is to predict the enthalpy distribution. That means somehow the temperature of distribution. We want to make sure that is not getting hot in one side and the other not that much. We want to have a balanced distribution. We want also to predict the void fraction. That means the volume of space that occupies the void. We want to predict the how is distributed the power in the bundle. All these kind of things, we do it with subchannel analysis. It's a more detailed analysis. System codes are one-dimensional. They predict average. They take the average of that section and they give you the values. Subchannel analysis will give you more detailed analysis. If you want even more detail, then you go to CFD, computational fluid dynamics, and then you will have much better details about that. But I stay in subchannel analysis. It's good enough for the nuclear industry.
Okay,
I
so
love that.
subchannel analysis is actually pretty comprehensive, is what you're saying. It actually includes multiple subfields within it.
I will say yes, it's quite specific to the analysis of the fuel assembly, where you remove the heat of the core.
I see. But is that term subchannel analysis, is that also used on like the boiler side, like the shell and tube heat exchangers? Do they also use a field of subchannel analysis to describe heat transfer, or is this really just for nuclear fuel?
It's basically just for nuclear.
Okay.
And it also mainly for water cooled reactors, because the other type of reactors, they don't have the same geometry.
Got it. Okay, great. Okay, and then how has your research progressed over the years to today? Like, tell me how you came across, like, what was your evolution in terms of your research focus that got us to the topic of supercritical water cooled reactors?
Excellent question. Yeah, and I love it. It was about 2011 when Dr. Lawrence Long approached me, and he says, "Do you want to work in a supercritical water reactor?" And I say, "Yeah, definitely. That will be quite interesting."
Who is this that approached you? What was his position?
Dr. Lawrence Leong, who was basically he was the previous project lead of the SCWR project. And he told me, I told him, yes, definitely, I would love to work on it. But I didn't know exactly what was the supercritical water reactor. And he gave me my first task to design the fuel assembly with subchannel analysis of the Canadian SCWR supercritical water reactor. And it was a beautiful exercise. I used everything that I knew from my degree in Mexico, my master's. All my knowledge, I put it there: optimization of systems, subchannel analysis. And finally, about 6 to 8 months later, we found, or we completed that task. It was a very multidisciplinary exercise. I had to be in constant communications with the guys of fuel, neutronics, making sure that we meet all the requirements. But by the end, we managed to get all the requirements, and we had a fuel bundle. And it was amazing.
Amazing. Let me ask one quick question and one long question. The quick question is, given that it's a Canada project, does this mean that heavy water is the coolant?
No, this is
light water. Okay.
We have light water as a coolant, but is moderated with heavy water.
Okay, so similar to CANDU is where they have like the two different volumes of water.
That's right.
But you're just replacing the flow water with normal water. Is there a specific reason why not just use heavy water for the coolant as well?
Well, the heavy water is quite expensive. And
is it? Yeah. Is it? Is it relative to your fuel, like your neutronics, like savings cost, right? I mean, yeah, it might be expensive, but so is enriched fuel. And if you can cut down on your, how do those economics work?
To be honest, I don't have the specific numbers, but I know heavy water is extremely expensive. Okay. I know when I work in the CANDU nuclear power plant, there is a system just to collect the drops, literally all the leaks, they collect the heavy water. It is very, very expensive.
And is there a reason, if you're simply going to be using the heavy water as a moderator, why not just replace it with like graphite or something like that, like with like an RBMK would or something like, is there a reason that you still want to keep the heavy water in as a moderator?
One of the reasons is we have the experience with heavy water.
Okay.
That's something, and this is
so save a little bit of money, but still stick with heavy water. Yeah,
that's right. And because the project in the end, it has multiple goals. It was R&D to develop the Canadian SCWR, but also to maintain capabilities. We want also to, because you can see we're living a generational gap, and we want also to have some capabilities. That's the reason we continue also with the pressure tube design and heavy water moderated. And that is also like a way to maintain some of the capabilities here.
Great.
And actually, I love the fact that we use heavy water. It has plenty of yes, there are disadvantages, but also there is multiple advantages.
No, I like heavy water too. Yeah, I just yeah, that's why I was curious why replace the coolant, but I guess that makes sense. It's more prone to leak if it's being used as a coolant, and therefore it's going to be more expensive operationally. I get it. I get it. Okay, so now my longer question. That was my short question. My longer question is, when you came into this project in 2011, what had been the state of the prior work on this topic? Like when you did your background research to see what everyone else had done, how many labs had worked on it previously? How extensive was the research in Canada on this topic? What did the world that you walked into when you started your research, how full of information was it?
Well, actually, I was surprised. There was already a big chunk of information. In Canada. We call it Generation X project. Then there was already what we call it a Canadian supercritical water, but it was really a can-do type. It was still horizontal core, and it was basically just a pressurized can-do. But there were already some projects on materials, some documents on knowledge gaps on how to understand the thermohydraulics under these conditions. There was already, I would say, a large body of knowledge, but it was still like under development. And also because supercritical water was considered in different fields. I found some documents from General Electric from the 1960s where they also proposed a supercritical water reactor. And they had a program, and I found some universities in the US who also performed supercritical experiments in materials and thermohydraulics. Then there was already some
the universities in the US, was that recent research or is that long?
No, that was long ago.
Yeah.
Ago. And I remember they also participated in the SCWR project for some time, the United States. But then they little by little, they are not more active in this area. Right now, Canada, I will say, is one that remains active. Our colleagues from China and the European Union. We have a very interesting program with the European Union, call it ECC Smart. And ECC stands for European, Canadian, and Chinese contribution. We were working I would say, the three continents together to establish the design requirements for a supercritical SMR. We're trying to.
Who is the most, other than you, who is the most vocal advocate for this technology out there in the world right now?
I will say from the IAEA, there is a person called Tatiana Yabramovich. She has been really helping us with that. We are right now working on the third coordinated research project on SCWRs. She has been supporting this technology, I will say, for several years, and she knows quite well this technology as well.
So that's the IAEA. Any other labs, like university labs or research labs that do?
Well, in the US, there is one that is amazing, the University of Wisconsin-Madison. They're doing an amazing job on SCWR.
They are? Okay, I didn't realize that. Okay, great.
Yeah, they're still working on that, and it's quite interesting. They have amazing facilities. We have in Europe, University of Pisa doing thermohydraulic analysis, the Czech Republic, the RESH laboratories there. ECMAT in Spain, they're doing materials analysis. KAT, they're doing thermohydraulics in Germany. University of Sheffield, they're doing CFD and DNS analysis in England. The University of Nottingham, Romania. We have a few countries contributing and doing research on SCWR.
Okay, great. Okay, so that was actually a pretty good list of labs. Now I'm going to ask you to give me the other side of the argument. Why, like, that's a good number of labs, but I, who like study this field of nuclear energy, like as a profession, have only recently come across this as a viable pathway forward. I think it should probably be the pathway forward. But why? What do people say is wrong with it? What do people say is the downside of pursuing this?
Well, I think one of the biggest fears is what happened with Fukushima. That we know it's a really unfortunate accident.
Okay,
It
but
created.
let's rewind even before that. I want to know why people weren't more seriously pursuing it, let's say in 2010 or 2005. Like, then we can get to the Fukushima stuff. But I want to first understand why this wasn't like the main area of EPRI research, in terms of
Yeah,
like
no,
upgrading.
I may not have the answer. I can give you my opinion, but for me, what I can see is because nuclear reactors so how they last for several decades, and you cannot basically touch them because the licensing process is
Of
very
course, of
stringent.
course, of course.
The evolution of the reactors is
Of
very
course.
slow.
Okay. So that's a good answer for like the macro picture of why we don't
Right.
advance technologies. But I'm actually so quite curious as to why this hasn't been the leading candidate amongst advanced reactor technologies. Because there are a
Oh,
lot of people
yeah,
putting a lot of money into lead, molten salt, high temperature graphite, pebble bed,
that's
triso.
right.
But I just never hear about this pathway.
SCWR. No, I get it, and I follow you. And I have been discussing that with a lot of colleagues, especially one colleague in economy, Alberto. Here we have a very good discussions, uh, and we still do not understand. But what we know is that we live an age of distraction. And actually, he published, how can I say, some notes about that in a book. Because what happens, and we believe, is we're getting tons of information constantly with different type of reactors.
Right.
We get these thousand voices calling us, and we just get distracted, and all our energy is diffusing.
Yeah.
The interesting about this book, or what's saying about the age of distraction, is if someone comes and says, okay, I will give you something that is better, that is safer, and is cheaper, somehow people will start looking into that. And why? And the problem is, unfortunately, the nuclear industry has been promising cheap and safe reactors for decades.
Yeah.
And
I actually think that most nuclear, let's say nuclear entrepreneurs, the new people who are trying to like pioneer new paths in nuclear, actually don't ever want to build anything. They just always want to be chasing after a shiny object.
in
That's
the
my
end,
theory. But I do want to get back to, before we philosophize too much, I actually do want to get to like the technical substance. There must be some downsides, and these are the areas of research that people are trying to de-risk with this technology. Materials, I get it. Okay, you've got some more corrosion issues at higher temperatures. What else? What are some other like technical areas?
The technical one that and I agree that there is a challenge, but it's proven to be feasible, is it operates at high pressure. 22 megapascals is the supercritical pressure of water. Our design operates at 25 megapascals.
Okay, but coal plants operate at high pressures. Like we get it.
Well, but now the fashion is like saying, for example, molten salt operates basically at a very low pressure, and that's the selling argument that.
Okay, so I personally am not worried about the high pressures. Thicken up the wall vessel. If you're operating at anything above standard atmosphere, just make a thicker wall vessel and call it a day. So I'm not worried about that. What else should I be worried about though? Anything to do with like pumps? How are you going to move the coolant? Do pumps cavitate when you pass supercritical water through them? What's going on?
Because we have the supercritical fossil fire plants operating with that, and it has been proven
no problem.
Very safe with technology. To be honest, I think it's just about marketing. In reality, the technology, when we studied, yes, we have some challenges with materials. That's well known, but especially the biggest challenge in the material is to identify the cladding. That's the big challenge.
Okay, let's talk about that for a second. Why is Zircaloy 4 not good enough to operate at let's say 500 C water? I'm not saying we have to go all the way up to 700, 800. Let's just say 500 for the moment. Why is it not good enough?
Well, the challenge with that is that Zircaloy deteriorates at those temperatures and conditions. It just simply, we put it and
I thought that Zircaloy's like oxidation potential really only kicks into gear after 700 C and doesn't really oxidize till 1100 C. What's happening?
Well, we made some experiments and we put it in under supercritical conditions, and they didn't last long, not enough to be feasible for a supercritical water reactor.
Interesting. Okay, so it's so cladding is the issue.
It's that's the big issue, and we have been working on that for several years. We have 2 international round robin tests with different institutions.
And what's wrong with stainless steel? Because reactors, I get that you lose. There's more neutron. There's like a parasitic neutron effect with stainless steel. But they used to make reactors out of stainless steel before zircaloy. So what's wrong with just going back to stainless steel?
Well, actually, that's one of the candidates that we have, stainless steel 310. And we're working on it.
What else? Inconel, is Inconel any good, or?
We're trying another alloy 800H.
Okay.
We also tried alloy 625. We have a list of different cladding candidates. The challenge is they have to meet so many requirements. They have to withstand the harsh conditions of the supercritical water, but also they are subject to neutronics. Then the material can degrade due to the neutron flux.
Right. Yeah,
it can brittle, it can age, you can have a different corrosion mechanism. Then when you finally think, oh, I have one that it makes sense, and you put it in another test and it fails, it's like, oh no, here we go.
Okay, so materials seem to be the big issue right now.
Identify the correct cladding.
And why cladding? Why clad at all? Like, why not just like allow your fuel pellets to just kind of sit in a giant pool?
Well, the cladding, we needed to keep the fission products inside. We don't want to
why not just keep them inside? Why do you need so many barriers? Why not just keep the fission products inside the reactor vessel and say that's enough barriers? We don't also need cladding.
Well, I'm not sure that it will be very safe. I think that we need that.
But okay, can I push back on that though? Because in most postulated accident scenarios where you experience a depressurization of your primary loop, you have to assume a fuel clad gap release. You have to assume that you lose your fuel cladding integrity anyway, and those fission products are going to get out of your system. And so why do we focus on cladding? A large majority of the fission products are trapped inside the ceramic matrix. Like that technically is your first barrier.
That's right. That's the first. I have to be honest, I may not have the complete answer for that, but we have to maintain also the integrity of the fuel, like if there is any vibration, to keep it in place. Otherwise, if there is nothing that it will contain it, it will just simply probably.
Okay. What do we think about graphite tubes then? There are graphite heat exchangers that exist out there that you pass coolant through. What about just instead of a cladding tube that's metal, why not just a graphite cladding tube?
I'm not sure graphite will make it with the supercritical water.
Oh, you think it would eat it up?
Yeah, I'm not sure, but I know that there are some materials that supercritical water. One of the challenges is that is a solvent. Then we have to. It is a challenge, yes, but we have chemical processes to reduce that. But I'm not sure if graphite will be an option for that. I don't know how we'll interact with water.
Okay, what about so can you just actually describe to me the chemical or chemical and mechanical processes by which supercritical water corrodes a material? What is it actually doing? Is it the oxygen is just more prone to attack? Like what's actually happening?
I have to be honest, I'm not materials guy at all. I'm in thermalhydraulics. I don't know why exactly what happens. I know it's extremely interesting. I saw some of the pictures that they took of the molecule, the cluster of molecules and under supercritical conditions to see what is the effect. I have to be honest, I will have to ask somebody from chemistry to explain us exactly what happened.
No problem. Okay, so let's talk about the heat transfer potential then and why there's such an advantage in moving to a supercritical region. In these, okay, let me ask the question a little bit differently. Is this a direct cycle? Do you go straight from your reactor to your turbine?
That's right.
Okay. And then, so what is the ideal pressure and temperature that you've modeled getting up to that you feed into the turbine inlet?
It's 20 for the Canadian supercritical water reactor. The conventional size reactor is 25 megapascals with an outlet temperature of 625 Celsius.
625.
Right.
25 megapascals. And then is there anything unique about your steam turbine? Because you get so much higher on the pressure, do you not have to go as high on the low side, or what's the trade-off there?
Well, in this case, we really didn't touch much on the balance of plant of the turbine. We're uh, trying to use what is available in the supercritical turbines.
Okay. And then does this necessitate in a boiling water reactor, like a feed water pump, or is there some sort of like natural circulation that you're able to
No,
induce?
it will need some feed water pump. Yeah, it will
And
need it.
And why not switch to a natural circulation system, like an integral style PWR, but with supercritical water? Because you'd be able to by actually going to this like weird phase change territory, you'd be able to induce natural flow a lot better, I think. So why not
Right.
have an integral PWR that is supercritical?
Yeah, and actually, that's a very good question. And at some point, we want to study that with more detail. But there is some effects that happen under supercritical conditions with the heat transfer, and it's the effect of the buoyancy. At some point, we can have a heat transfer deterioration depending on the orientation, because it's so hot, and basically you have very little flow, and that will have an impact on the reactor. Then it is a very good question. Working on the natural circulation under supercritical conditions, that will require a little bit more of research in that area, because the buoyancy forces are much more stronger than in water.
Which is great. Like you want more buoyancy forces to
Yeah,
drive the pumping power in a natural circulation system.
that's right. But the issue is when you are close to a wall that is hot, and that it may create hot spots, because maybe the fluid it will not move that much. Or
Is this because
there will
you don't
be
have
two different
like laminar
forces.
flow issues, or what's the
That's
issue?
right.
Okay.
That's what we call it, laminarization of the flow. Because you
why
have,
not then just like create a tortuous path to deal with that or something?
that's something that we tried, and yes, we actually one of the concept used wire wrap in the fuel bundles that promotes turbulence, but still we notice it may not be enough. It will create some turbulence, but may not be enough to really help to decrease the margin and to avoid the heat transfer deterioration.
Interesting.
Oh,
And
that is quite interesting. It's very, very interesting, and there is still some work to do. And we're trying to use the experience that we have already with force flow. Yes, what we try to do is also to study the possibility of natural circulation in case of an accident and see how it behaves. But that's still an open gap that we're working on. And this next fiscal year for me, I will start studying natural circulation on the supercritical conditions.
great. Let's talk about the neutronic side for a minute if we can. I'd love to also understand like how do you respond? Like, does it have a better transient response when it operates in the supercritical region? Like, how does the void fraction coefficient, the temperature coefficient, and the Doppler effect like come into play when you're operating in the supercritical region?
Well, right now we're using the same as we have with the water cooled reactors, because we don't have more information about that. There's no information in nuclear at supercritical conditions. There are no nuclear libraries about that. But we hopefully this year will measure neutron scattering at supercritical conditions. That will give us a very good idea of what's going on at high pressure temperatures.
And what's your hypothesis going in?
Well, we hope that, how can I say, it will behave similar to what we know. Hopefully, we will not get any surprises. I mean, in terms of R&D, if we get one surprise, it will be great, because we're opening something new that we didn't know. That will be great. But this will be something that we have to do, and we are planning, hopefully, this year to start some experiments to irradiate and to measure neutron scattering under supercritical conditions. That will be.
And how do you measure neutron scattering? Like, we don't? So you're saying we don't have a good like cross section library for neutron, like the thermalization of neutrons at like 600 C right now?
Maybe I'm not sure what is the limit, but I know that high pressures, high temperatures, there is not enough information for that. And
Yeah.
for that, we need to get the how can I say, to perform experiments.
Yeah.
One of my colleagues here at CNL, she managed to get some neutron beam time in Australia. We construct the cell, and hopefully we'll be able to send it there and perform some experiments there. That will
And
give us much more confidence in the neutronic calculations.
and what about like historical experimental data? I feel like they did so much cool stuff in the 50s and the 60s before everyone got like uptight about research for nuclear reactors. Um, is there like a treasure trove of information that you've identified but haven't been able to access or declassify yet, but you know is out there?
Not really. I think most of the information is already declassified. Like I was able to get it through a few websites, no problem, because it was from the 1960s. There is no issue anymore.
Yep. Yep. Okay. Interesting. Okay. Yeah. So, how do you think when you get together with this, like, this international forum and you rattled off the various labs, when you guys get together, do you kind of like decide, oh, you like, in order to advance this forward, here are the topics that we need to explore. So you guys take this one, I take this one. Is that how it works? Or is it everyone just kind of does what they want and then comes back with what they've learned?
You made a very good point. I'm very fortunate to be the chairman of the system steering committee of the SCWR under the GIF program. And one of my goals is really coordinate the whole program internationally of the partners. It is not an easy task. It is quite complicated.
Why? Why? Because everyone wants to do what they want to do and they just don't want to listen.
Well, it is, you have different nationalities, you have different ideologies, you have different budgets, different languages, different, how can I say, objectives. Then sometimes you have to navigate different things and make sure that we all understand the same thing, that we're on the same page, and also understand that we may not have the same resources. Some countries, they may have more than others, and some they may just start just joining the group. Trying to put that together in a document, it takes time. What we do on the, for example, on the Generation for International Forum, we have what we call PMBs, or project management boards, where we draft a plan, like a 5-year plan. We have meetings together, all the participants. We discuss the areas that we want to advance, and we said who wants to participate in that area. We have a plan, a structured plan with deadlines, deliverables. Once we reach a consensus, that is approved and we sign it. That is, for example, for the Generation 4. We have also under the ECC Smart, we prepared the proposal, we prepared the plan, we submitted to the European Union, Euratom, and if they like, that's okay, then we can continue. But yeah, it is the work of several people brainstorming what we can put based on our facilities and capabilities.
What are the open debates, let's say within the supercritical water cooled community, the people who are like bought into it? What are the open debates on which direction it should take? Are people saying like are people arguing about the max temperature? Are people arguing about the materials? Well, what are the debates?
We have multiple, like you said, this is actually any nuclear reactor is a multidisciplinary exercise. You have to have all on board. And for example, right now, one of the big challenges is to set up the maximum temperature. Of course, materials, they will tell you, no, we want this one because it's quite comfortable, but the thermalhydraulics will tell you, no, you know what, we cannot reach that temperature. We pass it always. And that is always the debate. Even just to propose the right operating conditions can take some time.
Yeah.
But once you have this, you can really start the process. It's a very, very iterative process. And you have to be in constant communication. And to have a good general view of the nuclear power plant and how the disciplines are interrelated. Because sometimes you forget one variable that it may be quite important. And then you advance some time, and then you advance, and then you realize that you forgot something that it was quite important. Then you have to go back.
Yeah.
And these kind of things, it will slow down the research.
Yeah. Let me ask you another question. Is there a big difference in behavior? Let's say I were to look at PWR that is operating close to the supercritical point. So, normal PWR operating conditions, 2250 PSI, 315 C max or something. If I were to just bring that up, if I were to just take those conditions and just bring it up another 40, 50 degrees, so I'm like just barely in the supercritical region, would you see a lot of the same problems emerge, like material problems, or do the problems grow linearly with temperature? Or is there like something really distinct about once you cross that triple point?
Yeah, there is actually the things change drastically. The properties of water change dramatically from passing from the subcritical to supercritical. And closer you get to the supercritical point, you get a lot of instabilities there because it's not you are changing to a different state. Then it's not that straightforward. You start having there is actually books that they just call it thermalhydraulics near the critical point, because
Really?
when you start getting when you start getting close to that point, the properties start changing a lot.
Can you help me develop a physical intuition for this? How do I think about the molecules as they approach the critical point and go past the critical point?
That's something that, be honest, I have been wondering, and it's difficult because to really visualize that at that pressure is not that easy. But what I can see is that the pressure is high enough that there is no surface tension, then there is no physical distinction between the gas and the liquid. They're just like a kind of a molecules with different densities. It's like if you had gases at different densities.
And do these, how intermixed are these different densities? Do they form like pockets and clusters? Like if I were to like look at it like a color chart, would I see like, things that look like water, be everywhere, but then like little pockets that kind of look like gas, or would it be
That's right.
evenly distributed?
To be honest, I just saw a few pictures of what's going on, and that's something that even the scientists are trying to see how they are distributed. But there are a few pictures out there, especially I believe one of my colleagues from China, he's specialized on that, and he took a few pictures, and you can see some cluster of molecules just close to the wall that they are gas-like, and the other are like liquid-like. Uh, I have the feeling, this is my personal feeling, that they will quite mix very fast, that they will not remain like as separate entities, that they will just mix. But because we have localized heat, then you will have also localized effects.
Yeah. Are there other fluids that are supercritical near room temperature that we can use as proxies to analyze that and then guess how the behavior of water might be?
Well, yeah, actually, that's another very good point. Supercritical conditions, it depends on the fluid. And yes, there are some fluids that, how can I say, that they can be at supercritical conditions at atmospheric pressure. But the challenge here is the reason we're operating at supercritical conditions is to take advantage of the heat capacity of the fluid to absorb that. And that is happen only with water. If we go with another fluid, we will not have the same effect. It will be probably the heat capacity will be very different. We may not be able to remove all that heat. For example, some fluids, especially some that there are mixtures, they start deteriorating or splitting in different fluids after a certain temperature. Water, the beautiful is that is universal, and it's proven to be very stable.
Yep. Yeah, I know. Water is an amazing coolant. It's amazing.
It's basically neutral. It's easy to work with, and that's the reason we have a very like a lot of plants in the world. They use water as a solvent for everything. Yeah.
I know. I just never understood this idea of moving to other coolants when it's like, I always say that if it was a good idea to use a different coolant, the coal industry would have used a different coolant. Like they
Yeah.
really care about efficiencies. They really care about like engineering, like improving the engineering of these plants. If it was a good idea, they would have done it.
I have look. I'm very lucky to have the hands-on experience in practical work and also in R&D. And I have to be honest, R&D problems, they are not that difficult as the engineering problems. These guys, they have to really make it work. As a scientist, we always estimate, we make things, oh, it's almost a circle, things like that. In the engineering world, you have to make it work, and there are tolerances. The pipes corrode, they deform, and that is a challenge. And if you find a fluid that is friendly to use, that is neutral, that is not toxic, you go with that.
I know. And then just remind me, you might have already said this, but has anyone ever built a research reactor that operated in the supercritical region in all of history?
Not exactly that I'm aware, but there was a few reactors that they operate at what we call superheated temperatures. They call it, actually it is the wrong name, but they call it that way at that time, on the supercritical temperature. And one was in Russia, I don't remember, I cannot pronounce exactly the Russian name, but it was functional for several years.
And this is just where they had like separate compartments or channels and then passed like steam through those channels or something.
That's right.
Yeah,
right.
that makes sense to me. It's like,
yeah. I mean, at some point, the nuclear industry, I guess, in the beginning, in the 60s, they try all different of concepts. Like you remember that they tried everything, and they tried to use nuclear reactors everywhere. I saw that they were trying to put them in airplanes and cars, and like, wow. It was a boom, and they tried different options, different technologies.
Yep.
And in the end, the water cooled reactor was the selected technology.
Yeah, I know. It's funny, you know, I feel like a lot of people who try to advance alternate coolant technologies say, oh, the only reason that we have water is because the Navy, you know, forced us to, you know, like Rickover forced us to use water. And I'm like, that's so crazy that you would say that. Like, that's the
right.
only reason. Yeah, not all power plant operating experience ever. Like,
and I know what you mean. That's the reason I started the conversation about what is critical about supercritical, because I received the same comments about, oh no, we will never operate a supercritical water. It's just above. That will never happen. And when I told them, you know, that supercritical fossil power plants existed since the 1960s, they're like, oh, really? They're like, wow, they exist, and they have been operating safely for years, decades. It's not a new technology. It's new in the nuclear reactor, but in the power system, it's quite old.
Yeah,
you are right. There is still a lot of things that we have to clarify. For me, when if I put in my how can I say it, like they say in English, if I put my hat of an engineer, I say keep it simple.
Yeah, keep it simple. Oh, that's exactly what I say. And all the best engineers say that too.
Yeah, keep it simple. Don't try to come up with very crazy ideas, because in the long run, it's difficult to control, and sometimes you cannot even build it.
Yeah. Okay, well, as we wrap up here, maybe I'll ask, you know, maybe two questions for you to wrap up with. One is like, is there a realistic plan that you think you might get one of these built someday, and when? And then the other question would be just like, what's your vision for the future of nuclear more broadly?
Well, I really hope so. And that's one of my challenges alongside some of my colleagues on the GIF. We want to really to have discussions with the water cooled nuclear reactor industry to really help us to identify, to clear a path for this technology, because we believe it has several advantages, like like I mentioned before, if we can replace the old fossil boilers, supercritical boilers, with a nuclear reactor, supercritical reactor, it will be a win-win situation. Like, I mean, it's not that straightforward but it is feasible, and we want to really see if that works. But for that, we need to build a prototype and see if that is actually a feasible idea and if it's also economical idea. But for that, we need the support from the industry as well. And that's one of the things. When it may happen, we don't know. Right now, as you can see, the new advanced water cooled reactors basically are still a downscale version of the generation 2 reactors. They just make them smaller and with enhanced safety systems. But in terms of efficiency, gain of increasing the temperature and all these kind of things, very little. And I believe we have right now, we're living a transition right now. And I think this is the right time if we want to implement new technology in the nuclear industry. The nuclear industry is a slow machine because it takes years to build the reactor. You cannot touch it. You have very little opportunities to really bring innovation to that. And I believe this right now we have that opportunity. I think we have to take advantage of it.
Yeah, absolutely. Well, thank you so much, Armando. This has been just a great episode, a great educational experience for me. So thank you for sharing this with us.
No problem. Thank you very much for the opportunity.
And initiate at least a new approach to the many difficult problems that must be solved in both private and public conversation if the world is to shake off the inertia imposed by fear and is to make positive progress toward peace.